Okay, so the next thing that we're going to do is take a look at, we'll do a quick review on gases, which is one of the physical states that you would have learned about in Gen Chem 1. So in order to understand gases, one of the theories that we use a lot to explain the behavior of gases and just matter in general is we use something called the kinetic molecular theory. And this is often abbreviated as KMT, kinetic molecular theory. So really when you think about what it means, the name kind of tells you what it is referring to. So there are different parts to the theory. We're just going to focus in on a couple of these. The first part has to do with the kinetic, right? So kinetic means that things are in motion, and specifically gas particles themselves. So these can be molecules, they can be atoms, they can be ions, whatever the gas particles are. These are in constant motion. So they're zipping around, they're moving around always, um, not just constantly, but they're also doing so randomly. So random motion, constant motion. And when they do that, these particles, these gas particles are going to exhibit specific types of behavior that we can use to predict some of the properties of our gases, right? So this is the basis for the kinetic molecular theory. Gas particles, right? And these, again, they can be atoms, they can be molecules, which are atoms that are combined together. They can be ions. We just lump them together and refer to them as particles. So if I have a container with some gas particles in it, okay, just imagine that these are my gas particles here. They're zipping around this container, constantly moving around, a great deal of speed associated with their motion, and it's also very random. Okay, so the other thing to note about these gas particles is as the temperature increases, so if we were to raise the temperature of this container, the kinetic energy of the particles will increase as well. Okay, so if you remember back from Gen Chem 1, temperature is just a measure of the average kinetic energy of a sample. So this then should be fairly intuitive in terms of how temperature can affect the motion of the particles. Now, when these particles, as you can imagine, they're eventually going to run into each other. So when the particles collide, they bounce off each other. So you can think about it like, if you're playing pool on a pool table, and you take the cue ball and you hit the other balls with it, well, they bounce off, right? They don't just combine together. They don't just kind of smash into each other and make a bigger ball. No, they bounce off of each other. And that's exactly what's going to happen with the gas particles. And then the other thing to note here is when the particles uh, collide with the walls of the container. So for example, when this one here, when it hits that wall, it will exert a force on that area. And that force that is exerted on that area is something called pressure, right? So P, pressure, is mathematically equal to the force divided by the unit area, right? And that's how we define it. So all of these are part of the kinetic molecular theory that helps us predict and describe the behavior of gases. The other thing to note for your gas particles and the KMT is that the gas particles themselves are incredibly small compared to the volume of the container itself. Okay, so the volume of the gas particles is negligible compared to the volume of the container. So in other words, right, we can say, and because the gas particles are moving around constantly, the gas particles will actually expand to fill the volume of the container. So the volume of the container is equal to the volume of the gas. We can make that assumption based on everything we talked about previously. So the volume of the particles themselves are negligible, meaning close to zero, compared to the volume of the container. So that's if you have to describe or remember or predict the behavior of gases, you can always go back to these ideas of the kinetic molecular theory to explain and predict gas behavior. So a couple things to note, a couple additional things to note about gases in general. So as we know, gases are all around us. So we can say they are ubiquitous. We find them all over the place and different, they come in different forms and in terms of, the particles themselves. So they can be atomic gases. So for example, something like argon or helium gas, they exist as individual atoms. We can have gases that are made up of molecules. So for example, oxygen, diatomic molecule, carbon dioxide gas that you're breathing out. Those are examples of some of the more common gases that we're going to encounter. Now, some elements on the periodic table, just as a quick reminder, so we're going to say recall the diatomic molecules um, that we talked about in Gen Chem 1. So for example, we had hydrogen, we had nitrogen, we had oxygen, we had fluorine, we had chlorine, bromine, and iodine, right? These are all diatomic molecules. They're not all gases, but the majority of them are. And they're diatomic as well. There's 3, 4, 5, 6, 7 of these that we mentioned um, back in Gen Chem 1. So we'll say the majority are gases. Okay, so gases are all around us. And they're also in us, right? Because we breathe in oxygen, we produce carbon dioxide, etc. So let's take a look at some of the things that we use um, to describe the behavior of gases. So these are the four, we'll call them properties. Some of these you've seen before. So for example, we have the volume that a gas occupies. So volume is abbreviated V. Typically, because the volumes of gases are usually large, typically liters is the unit that we use, but really it could be any unit of volume. We have the amount of a gas, which is abbreviated N, and this is usually in number of moles. We have the temperature, abbreviated T, and for gases, and specifically for the gas law calculations, okay, the temperature needs to be in Kelvin. Okay, and just as a quick reminder, the Kelvin temperature is the degrees Celsius temperature added to 273. It's 273.12, but just as a rounding measure, it's degrees Celsius is 273. So for example, 0 degrees Celsius is 273 Kelvin. And then the next one is pressure, which we just talked about. So pressure is abbreviated P, and this can have various units as well. We'll see atmospheres, ATM. We'll have millimeters of mercury, mmHg. We'll have torr. We'll have pounds per square inch or PSI, etc. Right? So there are many different units of pressure that you're going to encounter. And as a quick reminder, 1 atmosphere, which is what you experience at sea level, that is exactly equal to 760 millimeters of mercury. okay, which is exactly equal to 760 torr, T-O-R-R, and 1 atmosphere is also about equal to, not exactly, but approximately, that's a squiggly line, means approximately equal to about 14.7 or so PSI. Okay. So you will see several of these pressure units when you encounter some of um, the review questions. Okay, so let's take a look and see how these variables are related to each other via what are known as the gas laws. Okay, and when it comes to the gas laws, really, this is just, as you probably know already, there's a lot of math in the chemistry that you've seen so far, and this is no different. So really, these are mathematical relationships between those variables that we looked at above. And really what this, in order to solve these gas law problems, really what you're doing is a little bit of algebra to solve for an unknown. Okay, so that's what it boils down to in the majority of cases. So let's take a look at some of these relationships. The first one is the pressure volume relationship. Okay, and this is known as Boyle's law. Okay, and the pressure volume relationship is an inverse relationship. We can say P and V are inversely related to each other. So what that means in a practical sense is as one goes up, the other one goes down. So as pressure goes up, the volume goes down. Or the opposite would be true. As pressure decreases, the volume should increase, right? So that's what we can predict based on the inverse relationship. So when we look at these relationships, we're looking usually at comparing two variables, all the others, so the other variables, the other properties will be held constant. So N, we have not changing the number of moles, we're not changing the temperature, right? We're keeping those constant. So as P goes up, V will go down, or as P goes down, V will go up as well. So mathematically, this can be expressed as P1 V1 equals P2 V2, where P1 V1 is the product of the initial pressure times the initial volume. So these are your initial conditions, is equal to the product of the final pressure times the final volume, right? So what you end up with, pressure volume, should be equal to the product of what you started with, pressure times volume. So we can solve this equation for any of these unknown in that equation. And that's really what most, if not all, of these gas law problems are going to end up doing. Now you have to extract that information from the question that's provided, but that's really what they kind of all boil down to. So that's the PV relationship. The other one we'll take a look at here is the VT relationship. Okay, and this is Charles's law. Okay, and this is a direct relationship. So V and T are directly proportional to each other. So in other words, as the temperature, for example, goes up, the volume should go up as well, or as the temperature goes down, the volume should go down as well. Mathematically, this is expressed as V1 over T1 equals V2 over T2. Okay, and again, the subscript ones represent initial conditions on the left side, final conditions on the right. Similarly to the one above, you should be able to manipulate that equation to solve for any of those unknowns. We also can have the pressure temperature relationship, so the PT relationship. This is also a direct relationship. So these are directly related. So in other words, as pressure goes up, temperature would go up, or as pressure goes down, temperature should go down. Okay, and we can express those mathematically as P1 over T1 equals P2 over T2, just like the VT relationship. We have the volume and amount relationship, V and N. This is also a direct relationship. These are directly proportional to each other, directly related, sorry. So as one goes up, the other one will go up as well. So as the number of moles of a gas increases, the volume that gas increase will that gas occupies will increase. And then similarly, the opposite would be true. As the number of moles or the amount of the gas decreases, the volume that it occupies will decrease as well. Mathematically, V1 over N1 equals V2 over N2. Okay, and again, being able to solve for any of those you should be fairly proficient at doing that. We have what's known as the combined gas law as well. Okay, and that's where we combine three of the terms. So this is the P, V, and T relationship. And that relationship expressed mathematically is P1 V1 over T1 is equal to P2 V2 over T2, right? And if you just take a look at this, it actually has a couple of the gas laws embedded in it. If you kept the temperature constant, in other words, if T doesn't change, then you have P1 V1 equals P2 V2. That's Boyle's law. If you kept the pressure constant, right? So if P doesn't change, then you have V1 over T1 equals V2 over T2. That's Charles' law. If you kept V constant, if you didn't change V, then you have P1 over T1 equals P2 over T2, etc., and so forth, right? So that's the combined gas law. There is one gas law that actually has, just like the combined gas law, there's another one that actually has all of the other gas laws embedded in it, and that is known as the ideal gas law. Okay, and that is, if there's one gas law that you should commit to memory, it would be that one. And that gas law has all four of the variables, and it goes like this: PV equals nRT. Again, P is pressure, V is volume, N is the amount, T is the temperature. R here is called a gas constant. Okay, it's a constant, so it doesn't change. And that constant, there are a couple different values, but the one that we see most frequently is 0.0821 liter atmosphere per mole Kelvin. So if you were to use this gas law, right, you want to make sure that you have the correct units for each of the variables. And then similarly to the other gas laws above, you want to make sure that you're consistent with your units. Remember also, when you have T, when you're dealing with temperature in your gas laws, you want to make sure that that temperature is always converted, that you always have the temperature in Kelvin. All right, so this has all four of the variables in it, and I'll just show you really quick. If I were to rearrange that equation, what I end up with is PV over T is equal to N times R. Okay, I just divided both sides by T, and that gives me the relationship between pressure, volume, and temperature. If I keep R constant, which we know, I just told you that it is a constant. And if we kept N constant as well, if I didn't change the number of moles, well, then I have a constant N now times another constant R. Well, then that's just going to give me a brand new constant, right? So just a different number that doesn't change. This here is the same relationship as we saw above. So that's just one example where you can take that ideal gas law, ideal gas equation, and it has every single one of those other gas laws embedded in it. Okay, just by keeping some of the variables constant, we can derive any of those gas laws. Okay, so Those are the most important ones that we want to remember back from Gen Chem 1. And again, I didn't go into any examples with these because really what they boil down to is just math and doing a little bit of the algebra. The most challenging thing that students encounter with the gas laws is just organizing the information. Okay, so organize the information given, or the information presented. Okay, so you need to ask yourselves, what is the final? What's the initial conditions or values? Okay, and then most importantly, what is the unknown that you're trying to solve for? Okay, and as you probably know, because you've gone through this process already, half the battle in most of these problems that you're going to encounter is actually trying to decipher what the question is asking you in the first place, right? And what's going to help you do that, and that's going to be the same case for when you get into more Gen Chem 2 stuff, is organizing the information. What are you given, and what is it that you need to solve for, right? So that's something that I always tell my students, and from basic introductory chemistry classes to the most advanced ones. There are three questions that you want to ask yourself when you have to solve a problem, whether it's math, whether it's chemistry, whether it's biology, whether it's anything else. First question is, what are you given? Okay, so that means you need to read the question, extract the relevant information. Second question is, what do you need to calculate? What do you need to solve for? Okay, and again, organizing the information is going to help you do that. And the third question is then, how do we link those two? What you're given, what you need to calculate or find. Well, then the third question is, what are you going to use to solve? Okay, so in other words, what equation, what relationship or relationships, if it's a multi-step process, and if you approach every single question with those three questions in mind, uh, at the very least, you're going to be able to have some idea of where to start. And that is often a big roadblock for students, especially if you're, kind of reminding yourself or, it's been a while since you've taken a chemistry or a math class or something. Just organizing the information is very, very important. That's going to be helpful not just in our class, but in every single class that you take, whether it's chemistry, math, biology, whatever.